This is module 4, which will help you to understand the effect of input resistance on low frequency response of a common emitter amplifier system. So objective behind working on this is to understand the effect of source resistance on the cutoff frequency FLS due to the coupling capacitor CS. Secondly, the cutoff frequency FLC due to the coupling capacitance Fc. Thirdly, the cutoff frequency FLE due to a bypass capacitance CE. Here in this particular system, we'll study the effect of coupling capacitance CC on the cutoff frequency as well as the gain of the system. So this is your system, which is a voltage divider CE amplifier, and here it is represented in a block diagram form. So we are effectively taking this particular RC network to study the effect of CC on the CS on the system. So before going to that, first we will find out whether the system is stable or not. In general, when we are doing the practical consideration, we take that the system is stable. So based on that, we'll go ahead. So second point is we want to find out the input resistance Ri. So we go on to an AC analysis. So this is a RE model of the system, and which shows that input resistance Ri is a combination of R1 parallel R2 parallel beta Re. So second step, I have found out the input resistance Ri. So because of this Ri, what is the effect of this RC combination on the system? Let us try to study. So before going, because we are going to find out the gain of the system, so we are finding out this voltage VB, which is by voltage divider ratio. So Ri into Vs upon Rs plus Ri, and the admittance of this is J times Xc. So after rearranging the equation, I get something like this: 1 upon 1 plus Rs by Ri minus J times Xc upon Ri. So you rearrange in such a term that you get a magnitude part and a phase part. So that phase part is considered, and we are going to find out the frequency from this phase part, Xc upon Ri plus Rs, which turns out to be giving you the cutoff frequency due to Cs. So 1 upon twice pi Ri plus Rs into Cs, that is the cutoff frequency. We'll understand the effect of coupling capacitance over the gain. Now we have already found out the cutoff frequency, so how it is affecting the gain, let us try to understand that. Here this modified version of the equation you take, which is contributing to magnitude and phase part both. So what you do is you separate out these terms, all right, that is here it is inversed. So numerator is denominator is brought to numerator and so on because of inverse proportion. And this gain which is calculated, this is at mid-band frequency. So at mid-band frequency, this frequency is equal to FLS. So we get this relation, which is nothing but directly equal to the magnitude part, and here phase part is 0. So AVS is equal to Ri upon Ri plus Rs directly, wherein the cutoff frequency is given by 1 upon twice pi Rs plus Ri into Cs. So input capacitance in this present condition is Rs plus Ri, and capacitance C is Cs. So what we are doing is directly we are taking the RC combination at the input side and analyzing its effect at cutoff frequency and frequency below the cutoff frequency. So the mid-band gain is considered as 70% of the mid-band frequency. So it comes out to be 0.707. gain at mid-band, mid-frequency. So impact of frequency due to bypass capacitor CE. The same procedure is followed as you have done for CS. The cutoff frequency due to CE, we calculate the resistance RE by using this arrangement. Then your output side, this is beta times IB. R0 then load RL, fine. Then this is connected to your resistance RE. Now when you are calculating the effect of CE, what we do is we try to find small re across this emitter terminal. So this RE is nothing but equal to capital RE in parallel combination of RS dash by beta plus RE. So RS dash is this whole combination, which is shown over here. RS dash is RS parallel R1 plus R2. Fine. So in this way you get an output impedance that is RE, which is representing your R in this present combination, and CE is nothing but C. So in general form you can write frequency is equal to 1 upon twice pi RC. So in analysis procedure you don't have to memorize all these relations. You just remember that F is equal to 1 upon twice pi RC, and knowing whatever is the value of resistance and capacitance, you substitute them in the relation. So there is no need to actually memorize it. So next is effect of capacitance CS on the frequency. So what we do is you take an output side here and try to find out what is the load. So R is nothing but equal to R0 plus RL. So it actually R is a parallel combination of R0 and RL, which comes out to be this much approximately. So here this is R and this is C. So it's very simple, you don't have to memorize all these relations. So FLC is 1 upon twice pi R0 plus R into CC. Conclusion of the overall analysis. So due to inclusion of source resistance, the cutoff frequency FLS is reduced, but the cutoff frequency FLE is increased. Cutoff frequency due to CS at the output remains the same. Gain is largely reduced due to the voltage drop across the source resistance. So in order to understand the analysis, let us try to verify it by some example. So here what is given is that we have to perform the analysis with source resistance Rs of 1 kilo ohm and gain of interest region will be V0 greater than Vs rather than V0 greater than Vi, and we have to compare the result. Sketch the frequency response using a Bode plot for the following parameters. So Cs is given to be 10 microfarad, Ce is equal to 20 microfarad, Cc is 1 microfarad, R1 is 40K, R2 is 10K, Re is 2K, Rc is 4K, RL is 2.2 kilo ohms, beta is given to be 100, R0 is infinite. It's very important point to note, VCC is 20. So step to solve the example, use the DC analysis to find RE. Second step, find the mid-band gain, draw the RE model for AC analysis, find the input resistance Ri, find the cutoff frequency due to CS. Step 5, cutoff frequency due to CE. Step 6, find the cutoff frequency due to CC. And 7th step, plot the frequency response and find the effect of the various cutoff frequencies. Okay, so here we have drawn the system. Now we are finding out RE by using this DC analysis. First what we did is we found out the emitter current IE and then use the relation RE is equal to 26 millivolts upon IE. So beta RE is, find out what is beta RE. Beta is given to be 100. RE is calculated to be this much. So substituting that you get beta RE. Mid-band gain AV is the voltage drop. So RC parallel RL upon RE, which comes out to be 90. Okay. So input impedance ZI, here you have to draw the AC equivalent circuit. So R1 parallel R2 parallel beta RE, as we have done in the very begin of this presentation. So in that way you calculate Ri, which comes out to be 1.32 kilo ohms. Okay. Here the input side of RE model is taken. So input resistance is Ri, that we have already found out. So we'll find out the ratio of VB upon Vi. So VB upon Vs, this should be Vs. So you apply the voltage divider rule. So you'll get this VB upon Vs, which defines your voltage gain. Now here V0 upon Vi was given to you as minus 90, and that we have already calculated. So based on that you find out the voltage gain AVS. Fine. This can be expressed in dB. So in order to express this in dB, we'll be taking this is equal to 20 log AV to the base 10. Fine. So that you can do it yourself. So input resistance Ri comes out to be R1 parallel R2 parallel beta Re, which is 1.32 kilo ohms, and we have already used this. Okay. Next we'll find out the cutoff frequencies. So FLS is 1 upon twice pi RC. So input resistance is RS plus C, RS plus Ri. So substituting the various values, you get this. Similarly, FLC 1 upon twice pi Re plus Ri FLC, sorry, this is F0. This should be F0. So substituting this value, this is load resistance RL. So you get this FLC, which is at the output. Now coming to FLCE, RS dash we have found out. RE, small re is RE parallel RS dash by beta plus RE, and this comes out to be 24.35 ohms. So use this relation 1 upon twice pi RECE. Substitute the values. Let us see what value we get. FLE. So FLE is 227 kilohertz. Okay. So let us try to plot them here. So here your previous frequency due to the capacitance CS is 6.8 kilohertz, and accordingly these gains are taken and then it is plotted. Then FLC, because of the output cutoff frequency, this plot comes fine, and then due to the FLE, due to the capacitance CE is maximum among these three. So we consider the maximum of whatever is the cutoff frequency is calculated. So this is our actual required graph, which is an ideal, but in practical case the curve will turn out to be this way. This is your practical curve. This is what is required. So from this you go 3 dB down. So that will give you your mid band gain. Next coming slides, session of the present session itself will show you the animation showing you the effect of capacitance CE on the CE amplifier, and the next video shows you what is the role of RE in the amplifier system, both for DC and AC analysis.
In this animation, we will be examining the effects of a bypass capacitor on common emitter amplifier voltage gain. Here we have the basic voltage divider biased common emitter amplifier circuit. The circuit consists of 4 resistors and an NPN bipolar junction transistor. In addition to these core circuit elements, we are also using 2 coupling capacitors, which effectively block the DC element from the input signal as well as the output signal. The signal appearing at the input to this circuit is amplified and phase shifted by 180 degrees. Having assigned sample values to the elements in the circuit, we are asked how many times greater would the AC voltage gain of this common emitter amplifier be if a bypass capacitor was added to the circuit. We will begin our analysis by outlining the steps required to solve this example problem. We begin by calculating the base voltage for the circuit without the bypass capacitor. We then use the value of base voltage obtained from step 1 to calculate the voltage appearing at the emitter. The emitter voltage is used to calculate emitter current. Once we've obtained the emitter current, we use it to calculate the internal resistance of the transistor. Next, we use the internal resistance value to calculate the gain for the amplifier with and without the bypass capacitor. In the last step of the process, we compare the voltage gain of the circuit under both conditions. We begin our solution by calculating the base voltage for the circuit in its unmodified state. The base voltage can be determined by applying the voltage divider rule using the values of RA, RB, and VCC. When we substitute the known values and solve the equation, we end up with a base voltage value of 4 volts. We will now use the base voltage value obtained from our first step to calculate the voltage appearing at the emitter of the transistor. To do this, we subtract the base emitter voltage from our calculated base voltage to arrive at a value for emitter voltage. We use a typical value of 0.7 volts for the base emitter voltage to arrive at an emitter voltage of 3.3 volts. Moving on, we use this emitter voltage value with the value of resistor Re to calculate the current flowing through the emitter. This is accomplished by simply applying Ohm's law. This results in an emitter current equal to 1.32 milliamps. Having obtained the value of emitter current, we are now ready to move on to step 4 and calculate the emitter internal resistance of the BJT. The internal emitter resistance, Re, varies with current and is approximated using a 25 millivolt voltage drop and the calculated value for emitter current. We once again employ Ohm's law and end up with an internal emitter resistance value of 18.939 ohms. Having finally obtained the value of internal resistance in the emitter of the BJT, we are now ready to calculate the voltage gain of the amplifier circuit with and without the bypass capacitor. For the purposes of this demonstration, we will be using a simplified relationship to calculate voltage gain. This relationship disregards transistor beta. We will use the values of RC, the internal resistance of the BJT, and the value of RE to calculate voltage gain for the circuit. Substituting our known and calculated values, we evaluate the equation and arrive at a voltage gain of negative 3.176. Next, we calculate the value of the voltage gain with the bypass capacitor added, using the values of RC and the internal emitter resistance. With the capacitor in place, resistor Re is effectively bypassed for AC signals and does not contribute to the AC voltage gain calculations. Once again, we're using the simplified version of the voltage gain calculation that disregards transistor beta. With the absence of resistor Re in the denominator of our equation, the result of the second calculation is much greater than the first, and we arrive at a value of minus 422.409 as the voltage gain for the modified circuit. We are now ready to move on to the last step in our solution and compare the voltage gain of the circuit with and without the bypass capacitor. This is accomplished by evaluating the ratio of the two individual voltage gains. As can be seen by the result of this calculation, the voltage gain is 133 times greater with the bypass capacitor in place.
So the next video here will show you the use of emitter resistor in CE amplifier.
Now, what we have done is, we have used Re at the emitter, which will provide negative feedback in DC analysis, adding stability of the Q point. That is the use of Re in the circuit. It is very important to use Re in the circuit. I'll repeat that. Because of Re, the DC stability is increasing. But at the same time, we are having something called as AC analysis. So we must know what is the effect of Re during AC analysis. Now, this is a circuit diagram of transistor having Re or emitter resistor. What we have done is, we have short circuited all DC batteries present in the circuit. Now, circuit diagram will look like this. This is input AC applied or called as source voltage. This is actual input across transistor called as Vi, and this is feedback voltage across Re. Now, first of all, we will write about DC analysis. In DC analysis, because of Re, stability is increasing. Now, let's see what is happening in AC analysis. I'll apply KVL from base to emitter. If we apply KVL from base to emitter, we will get equation as Vs minus Vi minus Vf is equal to 0, and hence Vi is equal to Vs minus Vf. Now, I will write where Vs is source voltage, Vi is input voltage, and Vf is feedback voltage. So, where Vs is nothing but source voltage, Vi is input voltage, and Vf is feedback voltage. In this equation, Vi is actual input to the transistor, which is given by Vs minus Vf. But as IC increases, Vf will increase, and because of which actual input applied to the transistor, that is Vi, will decrease. This is very important point. If actual input to the transistor is decreases, then output voltage of transistor will decrease. Hence, output voltage will decrease. The main use of transistor is to amplify the signal, but we are getting less amplification due to presence of Re while AC analysis. Now, this is a very problematic case. We required Re, at the same time we don't require Re. Then how to deal with this? This is a very important question, because Re is added in the circuit to provide DC stability. If we remove the Re, then DC stability will decrease, and if we have the Re, DC stability will increase but amplification will decrease. To avoid this situation, what we can do is, we want Re during DC, but we don't want Re during AC. As simple as that. For that, we can do only one thing. We can add a capacitor in front of Re. What will happen because of that? Let's see. What I am saying is, suppose this is your Re or emitter resistor. Let's add a capacitor across it. The name of capacitor is CE. Now, during DC analysis, capacitor will be open circuited, and hence Re will be available. For DC, capacitor is open circuit. Hence, this circuit diagram will become means Re is present during DC analysis. For AC, capacitor is short circuited. Hence, circuit diagram will become like this. Now, if current is flowing, it will flow from this path during AC, because current follows minimum resistance path. If current is flowing from the Re or the emitter, don't say Re, if current is flowing from emitter, then it will be flowing from this loop, and hence Re as good as not present in the circuit, and hence amplification will increase. This is how we can bypass Re from the circuit, by using bypass capacitor at the emitter. This is the basic of bypassing Re from the circuit. We will bypass Re in order to get high amplification during AC analysis. Thank you.